Hello. In our previous class, we have studied linear ramp type voltmeters. What do we do there? Basically, we have input which is kept constant, and there is a ramp voltage which increases with time like this. It goes up, and at some point it crosses the input, and this time required for the ramp to cross the input tells us how large the input is. There we have seen a problem. The problem is that if suddenly the ramp say starts to increase faster than it is supposed to be, then we will think the input is smaller than the actual value. If the ramp becomes say slower, then we will think the input is more than it is actually. Okay. Similarly, the clock that we are using, the counter that we are using to measure this time, if the counter becomes faster, we will think more time has been elapsed. So, we will think the input is more. If the counter timer becomes slow, we will think the input is less than actual. To get rid of this problem, we will see a new completely new, not completely new, slightly new modified version where this problem won't be there. Okay. So, this is called a dual slope voltmeter. What do we have here? We have okay, for this we will need something new. We will need an integrator. Okay. Integrator circuit we will talk about later separately. For now, let us just understand what our integrator does. Okay. So, our integrator we will draw it like this, like op amp triangle. This is because the integrators can be made with op amps. Inside that we will put the integration sign. This is the input, this is the output. So, this is the symbol of an integrator. What it does? If I give the input as x t, then the output y t will be same as the integration of x t over time, starting from say some time, some reference time t equal to 0 to some time, call it, okay, let me call this t tau d tau. Okay, tau is the dummy variable. Okay. So, basically if say if input is like this, let me take an example. If input is like this constant, so this is x t, this is time, input is constant, how will be the output? The output will be like this. So, if it starts from this value, okay, it will then increase like this. This is y t. Okay. In general, we can also have a integration, a constant. The output can also be like this. This multiplied by some factor k. Okay. So, input multiply input. So, this is like just a multiplication of something. Okay. It's possible that the output is k times x integrated over time. K can be 1, k can be not equal to 1 also. Okay. And okay, also I can put a starting value to be more precise, more mathematically precise, where y 0 is this y 0. This is what an integrator does. Basically, if you have a step input or a flat constant input. So, over time, as time progresses, you see the area under it. So, initially this is area, and then as time increases, the area under it increases. As time increases more, the area increases, therefore, the output increases. That is what the integrator does. Okay. So, we will need this integrator. Okay. Then what we will do? We will take the integrator. This is the input, and we will have a switch here. So, this input can be connected either to this or to this. Okay. Then what I will do, okay. Now, these two inputs are, one of them is unknown, let me write V x, where V x is unknown voltage to be measured. And this called it V r. V r is a constant known reference voltage. Okay. So, we have these two things, and now let me connect a comparator here. Okay. So, what does this comparator do? It compares whether this value is higher than 0 volt or not. Okay. Okay. Now, from this we will drive a counter. So, this is the clock. We have to drive it through a AND gate like we did previously. So, from this clock generator, signal comes here and it goes to this counter. Okay. So, the counter will count when this value is logic high. This is a schematic only, you remember, this is not electrical circuit to be laid out exactly. So, this when this is high, you think it in this way, when this is high, then this counter will count. Now, what we will do, this is not yet complete. Okay, this is not yet complete. I will complete this as I tell you this story also side by side. So, the way we will measure is that call this K. Okay. So, step 1, connect or switch K to Vx. Okay, switch K to Vx. So what will happen? And Vx is a constant input. Okay, so if I connect this here, then this output will start increasing. Okay, so what will happen if this is say Vx, which is constant, then T versus call this y, Vy, then Vy will increase like this. Okay, it will increase like this, and assuming that it not assuming it is necessary that it starts from 0. Okay, so when you connect this switch K to Vx, okay, make sure that the comparator integrator output is 0. Okay, ensuring Vy is equal to 0 at this moment, at t equal to 0. Call this is t equal to 0. Okay. So what do? We first somehow ensure that the output of the integrator is 0. Okay. So this is 0. Then we connect the input to Vx. Therefore, the output will now start to grow from a value of 0 to some value. How fast will this grow? This will depend on the value of Vx. Okay. And if the integration constant is okay, I have already used k here. Okay, so there is a conflict of, so let me call this constant as c. Okay, c is the multiplication factor which gets multiplied with the input. So if this has this factor c, okay, then this I can write this as a function of time. I can write this is same as Vy is equal to c multiplied by Vx multiplied by t. Okay, Vxt is the result of integration of Vx over time, this multiplied by c. Okay, this is Vy. How it is increasing? It is increasing with time linearly. Okay. Now keep the switch to switch K to Vx, that means here, for a predefined time span. Call it T1. Okay. So let this output increase only for time T1. After that we are going to stop it. Okay. So Vy at time T1 will become how much? This will be, just let put this T1, C Vx T1. So this is how much this output will grow in time T1. Okay, right, fine. Okay. Now after that what to do? Step 2. Okay, let me do it here. this key to VR, which is a constant reference voltage. Okay, and let this VR be negative. Okay, so call it minus VR. Okay, so this is a negative value like minus 5 volt. VR is, if VR is 5, this is minus 5, minus 1 volt something. So then switch to this. Okay, now this is connected to this when at time t1. Okay, so at t1 bring this switch here. Okay, now what will happen? Now this output will, so now this Vy will be how much? It will now start to decrease. Okay, because now input is negative, and if you integrate a negative value, then the result decreases with time, right? So now the output will start to decrease. When it was here, okay, so assuming this was positive, so it was so the output was increasing. Now output will decrease. Okay, that's important. Previously it was increasing, now it is decreasing. So let's write now. So Vy will now become how much? So it will start with this value. Okay, so this is the starting value. Call this Vyt, then plus integration of C minus VR. Sorry, this is T1. Okay, then time minus T1 dt. So this is how it will increase, or you can write it like this directly. So this will be C VR, now VR is minus, okay, so minus C VR T minus T1. As T increases beyond T1, this value will continuously decrease. Let me also put the value of this from here. Okay, this is the starting value. So let me just put the value. Okay, so this is CVX T1, right? So this is the starting value, and then now it is decreasing. The question is, when will be Vy equal to 0? And one more thing, okay, so at this moment we are switching it, and we will also start this counter at t equal to t1. Okay, so let me write. So also start the counter at t equal to t1, or at t1 simply. Okay, and continue counting while Vy is positive. So Vy was positive initially at t1, and then it is decreasing, and so if it is decreasing, at some moment it will come to 0. So when will it come to 0? So say Vy will become 0 at t2. Okay, so therefore we can write Vy t2 is equal to 0 is equal to, from this let's write Cvx t1 minus Cvr, in place of t time I put t2 minus t1. So then when will it be 0? It will be 0 when, so this implies Cvx Vx T1 should be equal to C VR T2 minus T1. So from this you can write C cancels. So Vx can be written as VR T2 minus T1 by T1. Now you observe that VR is known, this time is a predefined time, fixed time. T2 can be measured. How? Using the counter. So that's why we said start the counter at time at this moment. Okay. So this counter can help me in measuring this time. Okay. So this can be measured. So therefore, so all these quantities on the right side, this is known, this is known, this is known. So this unknown can be found. Okay, from this, right? So this is the essential scheme in this measurement. Okay, let me also tell you to make it maybe possibly more clear. Let me explain this also again with some timing diagram. Okay. Let me keep it here for easy reference. Okay. Now let us see how Vy changes. Okay. So this is say time, and Vy will start from 0. So I write this make sure Vy is equal to 0 at time equal to 0. Then at this moment we will connect the integrator to Vx. So at this moment we will also connect the integrator at this moment. Okay. Therefore, Vy will start to grow. So Vy will start to grow from this like this. Okay. And at what rate will it grow? It will depend on the value of Vx. Higher the value of Vx, it will grow faster. Okay. Smaller the value of Vx, it will grow slower. Okay. And then let this be time t1. Okay. Now for t1, this is a predefined time. Predefined, pre-specified, okay, pre-specified time. Here connect the integrator to minus Vr, reference voltage. Okay. So now this is a negative value. Now the input is negative, so output will start to decrease. So the output will now start to decrease like this. And at some moment here, so this is the moment when the Vy crosses 0. Okay. So, this comparator is put here to see when Vy crosses 0. The purpose of the comparator is this. Okay. The moment Vy crosses 0, something will change at the output, which will tell, okay, this is the point when Vy is becoming negative. Call this time T2. T2 is to be measured. Measure this value, measure T2. T2 is to be measured. Okay. So, basically you have to measure this time, right. Now, from this what can we say? So, how much is this height? What can we say about this height? We can say, okay, this height is same as the slope multiplied by this time. So, this we can write T1 time multiplied by the slope, and the slope is equal to, slope will be equal to proportional to Vx and this constant C Vx. More the Vx, this will be higher, less the Vx, this will be smaller, and C is a constant of this integrator, which is a property of this integrator. Okay. So, this is this height. And if so, from this side, considering this side, what can we say about this height? We can say this is this time multiplied by this slope, right. So, how much is this? This height is therefore the same height. I can write now this time is T1 T2 minus T1 multiplied by this slope. How much is this slope? So, in this period this is connected to Vr. So, the slope is C Vr, right. So, from this side I can calculate this height to be C Vr times this minus, I can ignore because I am talking about the height, the absolute value. Okay. And from this side I have computed this height to be this. So, from this I can write T1 C Vx is same as T2 minus T1 C Vr, because this is the same height, and from which you can calculate the value of Vx. Right. So, this is the period when the integrator is connected to the Vx. Okay. So, connected to Vx here, and this is the period where it is connected to Vr. Okay. From this time measured, you can measure this unknown voltage. Okay. Right. Now, okay, and the important question here is, okay, now this is the important question. Important question is that we have to discuss, is this method sensitive to change in clock, this clock frequency, or some change in this integrator property. Okay. So, this is important question. Will we encounter any error if the crystal frequency say or clock frequency is erroneous, is changing with time slightly, or if the constant C, okay, this is a property of the integrator. Okay. So, this constant or in this equation this constant, if this is changing or if this constant C is erroneous, then will it lead to any measurement error, any error in the measured frequency? This is the question, and the answer is no. Why? So, let us consider first this constant C. Okay. Consider C. What happens if the value of C is increased? Means the integrator is changed due to some problem, due to aging or something, so that for the same input now the output will increase faster. Okay. If that happens, is that a problem? No, because what will happen is that both this part will increase faster as well as this part will decrease faster. So, their effect will finally get cancelled, nullified. You can also see this in this equation, where we see that okay, this constant C is in the both side and therefore, they get cancelled. So, even the value of C is changed, if C is changed by 1%, 2%, even more, this is changed in both sides, this cancels from both sides. Okay. So, therefore, C has no effect. So, C has actually no effect at all. Okay. C has no effect as it gets cancelled in the equation. What was the equation? T1 CVx is equal to T2 minus T1 CVr. Sorry. Okay. So, this has no effect. Now, consider crystal frequency. Okay. Okay. What is the role of the frequency of this clock generator? Okay. So, we do not have this frequency in any of these expressions. So, does it have any role at all in the measurement? Yes, it has. How? Because we actually do not measure this time T1 or T2. We actually measure the number of we measure the number of clock pulses in these two periods, here and here, or we see the counter value in this period and in this period. Okay. So, actually we do not have the value of T1 or T2. What we have is this, we actually have T1 is equal to C1 by F, where C1 is the counter value at this point. Okay. Say if the counter starts here, okay, then it will be the value of the counter here. Okay, or I may also start the counter here. I may not. So I withdraw my last statement. That may be confusing. So let me rather write where C1 is the number of clock cycles for which integrator is connected to Vx. Okay. So, for how many clock cycles this switch is connected to Vx, that is C1, and similarly T2 minus T1, this will be same as, call it C2 by F, where C2 is number of cycles for which integrator is connected to VR, reference value. Okay. And F is the frequency of this clock generator. Okay. So, basically here, therefore, you can actually write this is what? This is C2 by F, and this is what? C1 by F multiplied by VR. Okay. Once again, you see this F and F cancels. So, therefore, the frequency of the clock generator will have no effect. Okay. So, the frequency of the clock generator has no effect. Even if it changes slightly, absolutely no problem, it can change. Okay. Only thing, okay, what will change? Okay, no, so if the frequency is changed, say this clock, if this clock frequency changes, okay, it may change the time required for measurement. Okay, we will discuss it more later in the next class. Okay, but it will have no effect in the measured value. I should write no effect at all in the measured voltage. It can have other effect. Okay. Okay, so I request that you just think about this schema a bit. We will come back and we will talk about it more. We will take numerical examples so that the idea become more and more clear. Thank you.